Somewhere in the ocean right now, a great white shark is moving. It's been moving for hours. It will keep moving for the rest of its life, including while it sleeps, because if it ever fully stops, it dies. Not eventually, not after some long decline. For certain shark species, stopping means suffocating, in real time, within minutes. Compare that to almost any other animal on the planet. A lion can lie motionless in the shade all afternoon. A whale can hang nearly still in open water for long stretches. Even fish that look nothing like sharks can park themselves on the ocean floor for hours without consequence. But roughly 24 shark species, including some of the most famous ones on Earth, great whites, makos, whale sharks, don't get that option. Their entire survival depends on forward motion. So what's actually happening inside a shark's body that makes stillness lethal? The answer starts with something most people never think about. Breathing underwater isn't automatic just because you live in water. Fish, sharks included, breathe by extracting dissolved oxygen out of the water using gills. But extracting that oxygen requires water to actually flow across the gill surfaces continuously, so oxygen molecules can diffuse into the bloodstream. No water flow across the gills means no oxygen exchange, which means no breathing, regardless of how much water is technically surrounding the animal. Most fish solve this problem with a built-in pumping mechanism. They use their mouth and throat muscles to actively pull water in and push it across their gills, even while sitting completely still. It's called buccal pumping, and it works essentially like a set of internal bellows, drawing water in and forcing it out again in a continuous rhythm, whether the fish is moving or not. This is exactly the ability that certain shark species never evolved, or evolved away from. Species like the great white, the short-finned mako, and the whale shark rely almost entirely on something called ram ventilation instead. Their gills only receive adequate water flow when the shark is physically swimming forward with its mouth open, forcing water through by sheer forward motion. The same way sticking your hand out of a moving car forces air across your skin. Stop the forward motion, and the water flow across the gills drops towards zero. This is where this label obligate ram ventilators comes from. It's not a dramatic name for a mysterious condition. It's a precise description of an anatomical dependency. These sharks are obligated to keep moving because ram ventilation is their only functional method of breathing. There's no backup system waiting to take over if they stop, which raises an obvious question. If constant motion is mandatory, how does an obligate ram ventilator ever sleep? The honest answer is that these shark species don't sleep the way most animals do, and they definitely never go fully unconscious the way a mammal's sleeping does. Instead, researchers believe they enter something closer to a swimming autopilot state, a kind of restful, low alertness mode where large sections of the brain can power down or reduce activity while more primitive brain regions keep basic swimming motion running continuously in the background. The body keeps moving on something close to reflex, even while higher level awareness drops significantly. This is part of why sharks are frequently observed swimming in slow, repetitive circles or gentle patterns in certain locations, sometimes near underwater caves or specific current systems. Some researchers believe these spots may offer naturally oxygen-rich water flow, letting a shark maintain gill function with less physical effort than open water swimming would require, essentially finding the underwater equivalent of coasting downhill instead of pedaling uphill. Not every shark species is locked into this system though, and the exceptions actually help explain how the whole mechanism evolved in the first place. Species like nurse sharks and many species of bottom-dwelling sharks retain a working buccal pumping system, essentially the same active breathing muscles most fish use. These species can pull water across their gills manually while lying completely motionless on the seafloor for extended periods, which is exactly why you can find a nurse shark resting quietly in a reef crevice for hours without it facing any risk at all. Some shark species sit somewhere in between the two extremes. Certain species can switch fluidly between buccal pumping while resting and ram ventilation while actively swimming, essentially running two different breathing systems depending on the situation, like a car that can idle on its own but also draws in extra airflow once it picks up speed. This flexible approach appears most often in species that spend significant time both resting on the bottom and actively hunting in open water. So why would evolution ever favor the riskier, mandatory motion version of breathing at all when a built-in pump seems like the obviously safer design? The likely answer comes down to a fundamental trade-off between efficiency and flexibility. Buccal pumping requires dedicated throat and mouth musculature constantly working to force water across the gills, which costs energy even while an animal is otherwise resting. Ram ventilation, by contrast, essentially outsources that entire job to the shark's own forward momentum. For species that evolved to be near constant wide-ranging hunters, covering enormous distances across open ocean in search of prey that could appear anywhere, that trade-off made sense. Give up the ability to rest completely still and in exchange, gain a more energy-efficient breathing system perfectly suited to a lifestyle built around continuous, long-distance movement. This connects directly to body design too. Obligate ram ventilators, like the great white and the mako, are almost universally open ocean predators, built for speed, endurance, and covering vast hunting territories. Species with buccal pumping, like nurse sharks, tend to be bottom dwellers that spend much of their time in one general area, ambushing prey rather than chasing it across long distances. The breathing system each species ended up with lines up almost perfectly with the actual lifestyle it needed to support. There's a common myth attached to all of this that's worth addressing directly, because it slightly overstates what's actually happening. The claim that sharks will instantly die the moment they stop moving isn't entirely accurate for every species, and even for true obligate ram ventilators, death isn't always instantaneous. What actually happens is oxygen deprivation beginning almost immediately once forward water flow stops, followed by a rapid physiological decline as the brain and muscles are starved of oxygen. For a fully obligate ram ventilator held completely motionless, that process can become fatal within a relatively short window, but it's a physiological cascade playing out over minutes, not an instant mechanical shutdown the moment motion stops. This dependency also explains a specific and unsettling phenomenon called tonic immobility, something marine researchers have used for decades as a way to safely handle certain shark species. If you flip certain sharks upside down, many enter a temporary trance-like paralyzed state. Muscles relaxed, motion completely stopped. It's often used by researchers as a safe way to briefly examine or tag a shark. But for an obligate ram ventilator, tonic immobility comes with a real built-in danger. Extended immobilization can genuinely risk suffocation for exactly the reasons already described, since even a research-induced pause in swimming cuts off the gill's only water supply, which is why marine biologists working with species like great whites keep these handling windows extremely short and closely monitored. Interestingly, some predators appear to have discovered this vulnerability entirely on their own, long before humans ever studied ram ventilation in a lab. Orcas have been observed using a hunting technique where they flip certain shark species upside down, deliberately triggering tonic immobility. Once immobilized, the shark can't fight back or escape, giving the orca a completely safe, controlled opportunity to feed. It's a striking example of one predator exploiting another predator's most fundamental biological weakness, not through brute force, but by understanding in some instinctive sense? Exactly how that other animal's body works against it. So the next time you picture a shark endlessly cruising through open water, it's worth remembering that what looks like restless, predatory energy is actually a fixed biological requirement, not a choice. For species like the great white, movement isn't a lifestyle. It's the literal mechanism keeping oxygen flowing to its brain, one continuous stroke at a time, for the entirety of its life, with no version of standing still ever really available to them at all.